super high. And just a friendly reminder, it's the current that kills, it's not the voltage. And that was this is display. That's what I was trying to do.
Yeah.
To show y'all.
It's for safety.
Yeah.
It doesn't matter which way you put the resistor. Like
No.
this way or that way, or
Yeah, it doesn't matter. Okay, yeah. So current's turned down now. Yeah, that's why high current is very dangerous. That's why you don't stick like a fork in the power outlet. Okay. So, now let's get some potential. You have to give it some current. So,
It was all the way high, is that why?
yeah, the current was turned all the way up. Okay. So, I'm kind of standing in the way here, but you can measure the potential at any point here. So, if I want to measure like when it exits and leaves the circuit, we can get a potential across. And it should be about the same as what's measured here. And then we measure potential across a resistor by just doing the same process. And this one, it should be the same. Yeah.
Because there's only one resistor.
Yeah, there's only one resistor. And so you have the potential right here, and then it drops off. So on this side, it's like 4 volts, and then on this side, it's grounded.
Yeah.
Out. So 4, 0. You get a potential difference of 4. Okay. That's the one that's melted. So we're doing this one. So we'll do resistors in series. Okay. So now, notice I played around with it. I wasn't shot because the current's low like it should be. It makes it safe, to, even though it's on still. So again, like we can measure a potential across it, and it's around 4.3 or whatever. Now, if we look at each individual circuit here, I should have it backwards. That's why it's negative. But yeah. So we have a drop off of about 3 volts. So according to Kirchhoff's potential rule, this one then should be around 1 or 1.5 volts across. 1.2 or something. Yeah, 1.2 across. Yeah, and you notice you have, and I knew that because from Kirchhoff's loop rule. So the potential across our electromotive force is around 4.2 volts. I don't know why it's jumping so much, but and then from there we have a 3 volt drop off and then a 1.2 drop off to make it grounded again. Yeah. So the sum of all the potentials, and you can go from any point, and you get a net 0 potential change. And okay, now let's go. And also, you can see if I had a current sensor with me, I could show you that the current is the same across both of these guys.
In series.
Yes, they're in series. Current's in series. That's why when we hook up an ammeter, actually I should show you all this. It's important. Y'all know how to do the current part. So for these, hook it up into milliamps, and then you need to get another. I guess it doesn't matter, but it's always good to use black as your ground. and then turn the dial to milliamps. So we'll go on the scale of 20 milliamps and see what we get here. I might have to lower it some. This is the anode, this is the cathode. I'm going to drop it some. Oh. Yeah, I'm silly. No, I was just saying, you have to. Current is the same in series, so whenever you do a current sensor reading, you have to set it up to be in series. So you take the positive end, the anode, look at it right there, and then you complete the circuit. And what? This is not getting anything. I'm doing wrong. Bonus points, who can tell me? Yes. Yeah. Maybe I just got a bad one. Let's just try something else. It's fine, good.
Can you turn the amps off, the current off?
The current's flowing through it. It's just really small. It's in order of like milliamps. That's why it's not reading anything. No. You got a reading now. Next time I'll drop off. So I got a reading of 0.1. Okay, now I'll show y'all at 0. Hold on, let me try a different sensor.
Fluctuating pretty.
Mm-hmm. Yeah. I'm getting confused with.
You want coffee?
Yeah, I'm all black. Last one, and I guess a different current sensor. Excuse me.